colleagues in galaxies. They ask, how do galaxies get their gas? I'm going to ask, how do planets get their gas? And if there's anything I've learned in this subject, it's that thermodynamics is everything. To cool is to accrete. So you take a rock, you throw it in a sea of gas, it binds to itself gravitationally all the gas within its gravitational sphere of influence, otherwise known as the Bondi sphere, or if it's tidally truncated, the Hill radius, or the Roche radius. And if you want this proto-atmosphere to grow, you just wait. You wait for the gas to cool, radiatively. It cools, it contracts, and when it contracts just a little bit, it allows fresh gas to seep in from the outer boundary. And that's it. Okay? The rate of mass accretion is completely controlled by the rate at which this proto-atmosphere can cool. The mass increase time scale, right, is given by the Kelvin-Helmholtz time scale for the atmosphere. Right? How long it takes to cool, how long it takes to get rid of the thermal energy associated with this atmosphere of delta M, given a luminosity, a cooling luminosity through the atmosphere. That's all it is. It's passive cooling. And here's the one-sentence answer for why it is that percent by weight atmospheres are everywhere in the universe. So let me see if I can get it in one sentence. So, percent by weight atmospheres are everywhere in the universe because percent by weight atmospheres around super-Earths have cooling times that are measured in millions of years, which is the lifetime of the gas disk, which feeds the atmosphere, period. Okay, I don't know if that sentence was compound or not, but that's my answer, okay? That's the answer. You just set the cooling time of the atmosphere equal to the gas disk lifetime. Solve for the mass of the atmosphere, you get 1%. But now the question is, why is it so insensitive? Why is this number of 1 million years insensitive to what the outer nebula is doing? Well, it's because, Richard, do you have a question?
Would angular momentum of the gas also affect how...
Oh, well, in principle, as you go to larger masses, what are called super thermal, I don't want to get too technical, but yes, as you go for the giant planet phase, for stages, which is not this, then you have to worry about rotational support. But for these subthermal cases, for super-Earths, I don't need to worry about it because you're well in, yeah. But yes, rotation is an issue for giant planet formation, just not for these. Okay. Why is it so insensitive to rho out? It's because at the L, right, the cooling luminosity doesn't depend on the outer nebular density. It doesn't depend on conditions at the Bondi or the Hill sphere boundary. It doesn't even depend upon the photosphere. It depends deeper down. It's regulated deeper down at the radiative convective boundaries for these proto-atmospheres. Most of the mass in the atmosphere is convective. And if you know your stars, you know for bodies that are convective, it's the lid that matters, right? In controlling the vigor of convection. It's because convection is so efficient at transporting heat that the real bottleneck for luminosity, the bottleneck for energy release, is where convection breaks down, which here, in this case, convection breaks down where radiation takes over. Okay, so the luminosity is controlled deep into the atmosphere at the radiative convective boundary. And the density there at the RCB just depends upon the internal adiabat. It depends on internal properties, right? It doesn't depend on conditions out here. Okay, so, and this is just a demonstration of this, what we do these are just the solutions to the equations of stellar structure, right? Applied to these planetary atmospheres. And you have 3 different nebular densities, 3 very, very different nebular densities, 3 different rho outs, densities at the outer boundary. These are pressure temperature profiles, by the way, right? Really density temperature profiles. And you're going in this way. And all roads, no matter where you start, lead to this more or less the same RCB, the same radiative convective boundary. So it's the density and the temperature here which control L. I promised I would derive for you this law, how m gas scales with time. I can get really close in 2 lines, or 3. So the mass doubling time scale is just given by Kelvin-Helmholtz time, which you set equal to the time that has elapsed, right? This last equality, by the way, people write this down all the time to compute cooling curves for things like white dwarfs or brown dwarfs, right, that are passively cooling into vacuum. So it's the same problem here, except you're not passively cooling into vacuum quite. You're passively cooling into a bath, which then feeds you. So that's the difference here. Yeah?
That's only true if you're treating gas, but if you're treating full-size objects, they will puncture your convective radiative boundary.
Oh, you're talking about things like planetesimal formation, for planetesimal accretion, so
right.
Big rocks raining down into the system.
So
Yes, you can if you want. They just delay the whole process.
Right.
You have to wait because they're an energy source. You're heating up the atmosphere, preventing the cooling. So all of this is happening after the planetesimals have finished accreting. And it doesn't take very long for the planetesimals to coagulate onto the core, because the time scales where we see these even at 1 AU, they're quite short. So all of this is staged after the rocks have finished raining down. The numerator, the energy in the atmosphere to order of magnitude, given by the gravitational potential energy in the atmosphere. Okay, pretty simple. You should get 1 power of m gas. The denominator, the cooling luminosity, well, you evaluate it at the bottleneck, which is the RCB. So that gives you another power of 1 over m gas, because L cool from radiative diffusion goes as 1 over rho. And there's the rho gives you another power of m gas. So at the end of the day, you get m gas divided by 1 over m gas, which gives you m gas squared, goes as t, and so m gas goes as t to the 1/2. It's not quite 1/2, it's more like 2/5. That's because there's an extra finicky density dependence in the opacity, which it depends on your model. In some cases, it's controlled by H minus. Even in other models, kappa goes as rho to the 1/2. It's true for H minus opacity. And if you fold that in, you'll get your 2/5. And you can repeat this whole exercise to get any dependence you want. For any other variable. So gas mass fraction scaling with time, with core mass, with metallicity. It's really nice and simple. It's at the level, I think, of maybe an advanced undergraduate class. People told me once that if you can make it into a textbook, then you're done. So I submit this as a problem set for students to work out. It's really quite straightforward. Here are the analytic expectations. So gas mass fractions versus time, gas mass fractions versus core mass. Here's your 2/5 law. Here's your 26/15 law. Okay, and those are the analytic expectations. And I'm going to overlay on this the numerics, and they match up pretty nicely. So it looks okay. This is interesting. It actually falls off this straight up power law for really low core masses. When the core mass is so low that the atmospheres are so low in mass, they're basically done. You've maxed out. You can't grow anymore because you've cooled to the point where you're isothermal now with the background nebula, right? So we call them, you're too cool to cool further. So you're done. And so you drop off that cooling track and you're done. Let me tie this part of the talk into try to tie it into a bigger astrophysical picture. The theory is asking for a gas poor environment. Exactly how gas poor, I don't really care. Okay, just not 0. It does have to last for something like 10 to the 5, 10 to the 6 years. This is what we asked for. The universe responded and said, I think I have just the thing for you. And they're called transitional disks. Maybe. Gas poor, but not gas empty environments, okay, lasting on the order of 10 to the 5, 10 to the 6 years. I will make a bet with people, anyone, that there's a family of super Earths happily residing inside this cavity, happily accreting, building their atmospheres, siphoning off just a little bit of the accretion flow that must be supplied from the gas-rich outer disk. Gas densities inside the cavity, I've emphasized, should be so low that migration is not an issue. I'm going to end this part of my talk on super Earths by giving you one more line of evidence, independent, for why we believe formation was migration-free for the super Earths. It's using the occurrence rate profiles measured so well by people here and tabulated so usefully in your papers. Even I always wondered, though, why you didn't complete the exercise and plot your data. Well, we did it for you. This is what your data look like when we plot them. It's amazing. Number of planets per star versus period. Super Earths are everywhere, but mostly everywhere outside of about 10 days. The occurrence rates are high, and they're pretty flat in log period.